Good evening to all of you. In today's lecture, we are going to learn one more very important theorem of electrical science, which is known as superposition theorem. Last time, we saw what are the applications of Norton's theorem. This time we are going to see firstly, before understanding what is the superposition theorem, let's try and understand what are the applications of superposition theorem. Okay, erroneously this is written as Norton's here. So let's see what are the applications of superposition theorem. Right. So firstly, it helps in analyzing a linear circuit with more than one independent source. Okay. Here the key word is more than one independent source. Okay. Till now, whatever the circuits which we discussed, they didn't have this clause of there should be more than one independent source. This particular theorem is targeted towards solving circuits which has got more than one independent source. Okay. Whereas Norton and Thevenin, they could be a circuit which has got only a single source also, but that is not applicable in this case. By using this superposition theorem, we can find out the value of voltage or current in each of the circuit element. Okay, not only in one particular element, but we can solve this and try to find out what is the voltage or a current through a particular element of the circuit. Okay. So how we do that is we try to find the contribution by each of the independent source separately, and then we do an algebraic sum of the currents or voltages. Okay. So the output is determined by summing the individual responsibles of each of the independent source. So the idea of the superposition rests on linearity property. Okay, that means the circuit has to be linear, like that was the case for the other theorems also we did till now. Here also linearity is an essential property. Only then we can apply superposition, right? So what is linearity? Suppose you have a system and you are giving a input x1n, and then you have an output y1n, right? And now if you are giving a second input, alternate input x2n to the system, and you have a response of y2n. So if I give a combined input x1 and x2, the output should be this. As long as the system behaves in this manner, then it is called, it's a linear system. Okay. So the system has to behave this way, right? This is possible only when we have certain linear elements in the circuit. If we have non-linear elements in the circuit, then this condition will not be met. Okay. So let's see. Take an example. Suppose a current I is flowing through a resistor R, then the voltage which will be developed across that resistance will be V1. Okay. Similarly, this is the cos is I1 and the result is V1 here. Okay. Here again I am pumping in the I2 current into that resistor, and it will generate a voltage V2. So now what happens if I am going to supply current I1 plus I2 into the same resistor? Then the voltage will be V, and the that will be defined by I1 plus I2 into R. Now if I open up the bracket, it will be I1 plus R and I2 plus R. So that will give me V1 plus V2. So this only proves that the resistor is an linear additive element. Okay. So all the elements in this circuit has to be linear. So resistance is a linear element. Similarly, you can have inductors, capacitors or transformers. They will also be linear. Okay. Whereas an diode transistor, okay, those things, MOSFETs and those things are not linear. Those components are not linear, so we cannot use superposition theorem for that. So towards the end of the lecture, I will show you a video and explain you further that how diodes and all cannot be used for superposition theorem analysis. Okay. Another thing, so this is the superposition theorem. It says any linear bilateral network. That means you can't have elements which are direction specific, like diodes and all. Okay, even in that case it is going to fail. So it says linear bilateral network containing two or more independent sources. It could be voltage source or a current source. Not necessarily you should have two voltage source or two current source. It could be one voltage source and one current source. Okay, even that kind of combination is permitted. Then the resultant current voltage in any branch is algebraic sum of current voltages caused by each independent source with other independent source turned off. Right. So we can switch off the other independent source and switch on only one source at any given time and compute the current, and then we can do an algebraic sum. Okay. So suppose in a circuit you have three sources, then you can switch off two of them, take only one of them, find out the current in a particular mesh or a particular element, and then do it for the second source, and then do it for the third source, and then algebraically add it up. Okay, that is what superposition theorem states. Okay, so now this we have done in our previous theorems also, like a voltage source. When I have to remove that voltage source to see the effect of other sources, then that voltage source is shorted. Okay. Similarly, if there is a current source and I need to remove it, then I will replace it by an open circuit. Okay. So if there is an internal resistance, then the internal resistance will come here. Okay, for Vs, and similarly for Is, if there is an internal resistance in parallel, so that will come here. Okay, if it is an ideal voltage source and a current source, it will be replaced by a short circuit or by an open circuit. Okay, so this is, we need to know these things. Okay. Now it will be very clear once we take on some examples. Here a 6 volt is applied here. There is an 8 ohm and a 4 ohm. We need to compute the voltage across 4 ohm. There are two sources now here, right? So you can do that mesh analysis or node analysis which we have done earlier, but we will find superposition theorem is a much simpler approach. Okay. So if I see this out here, right, I have redrawn these circuits here. In the first case, this 3 ampere has been removed out here, right? So this, so directly if I have to write the voltage out here, how can I write that voltage? That is known as the voltage division rule, right? It is 6 volt and 4 ohm and 8 ohm. So 6 into 4 divided by 8 plus 4. So I straight away get the voltage what is available across 4 ohm. And if I have to find the current which is going into this 4 ohm, the total voltage is 6 and total resistance out here is 8 plus 4. So 6 by 12.5. So this is with the single source. So this is the condition, right? The current which is flowing, the voltage across the 4 ohm is 2 volts, and the current which is flowing into the 4 ohms is 0.5 ampere. Now in the second circuit, we need to remove this 6 volt. Okay. Now for a current source, we had left it open, and now we are going to remove a current voltage source. So we have to short it. Okay, so we are shorting it and we are retaining the current source. Now we need to find out what is the current and voltage across this current going into 4 ohm and the voltage across this 4 ohm, right? So now here we use the voltage division rule. Here we are going to use the current division rule. So division rule. So 3 amperes into 8. Like, right, that I explained to you last time also. Higher the resistance, more current will flow here. So that is why this 8 comes here in the numerator. So 8 divided by 8 plus 4. So you get 2 amperes current which is flowing here. Now the voltage across 4 ohms, that is Ohm's law, pure Ohm's law. That is 2 is the current and 4 is the resistance. So you get 8 volt. Now if I have to find out the total voltage when both these sources are working in conjunction, then simultaneously they are operating, then what would be the voltage? It will be just be an algebraic sum. So here we got 2 volt and in this case we got 8 volt. So we just need to add it up. So 10 volt. So 10 volt will, in this particular circuit, 10 volt will be the voltage which will be across the 4 ohms. Similarly, a current is here an 0.5 ampere. And here it is 2 ampere. So if you see the in both the, while analyzing both the circuits, the directions of the currents are same. So they algebraically they add up. So it comes to sorry, this should have been 2.5 ampere. Okay, instead of it's erroneously written as volt, so it should be 2.5 ampere. So it's a very simple technique, and many a times, at least I find, application of superposition theorem is much easier than many of the other theorems. Okay, okay, is it clear to all of you? Yeah, Gagan, is it okay? Okay, so let's move forward. So let's take one more example. Here we do have, instead of only independent sources, we also have dependent sources. Okay, so we will, when we apply superposition theorem, do remember that we cannot remove the dependent sources. Okay, independent sources only, not the independent sources will be removed, one each at only, retaining only one at a given time, but the dependent sources will always be there in the circuit for analysis. So it is not that we do we make 4 different circuits, one with 2 volt, one with this, and then this. Okay, so these 2 sources which are in the rhombus, they indicate they are dependent sources, so they cannot be removed. Okay, for analysis they will remain there in the circuit as it is. Okay, so let's take the case. In the first case, we are removing this current source 11 ampere. So this has been removed from here. Okay, so obviously if you see this circuit, and it has become pretty simple. See, the current now cannot, of this loop cannot go into there, because there is no path available for through and through current. So the current will, one current will rotate here and one current will rotate here, although there is a line out here. Okay, so any charge which is moving this side, it cannot happen because there is no return path available. So this equation is we need to write the equations of this and this and separately. Okay, now if you see 6I1, and when we do superposition theorem, we should not take the loop currents. Instead of, we take the currents of the individual elements. Okay, so that is one change with respect to the approaches which we had, which we studied till now, where we always took the loop currents. Here we need to take the currents in the individual elements. Okay, so this Y1 is the current which is flowing into this 1 ohm resistance, right? And now this is the voltage. So voltage is what? Current into resistance, and here it is 1. So I can write 6 Ix1 is equal to Iy1. So this is one equation I get. Now what is the second equation? Here it is again an current source. This is a current source, and this is the current. So straight away these two currents can be equated, because there is no other path for current to go out of this particular small mesh, right? So Ix1 is equal to 2I1. Now if you see 6 Ix1 is equal to Iy1, here Ix1 is equal to 2 Iy1. So these are two equations. They can be satisfied only if both of them are 0, right? So you get 0. Now we are interested in computing the voltage across these two terminals. So if you see that there is no current flowing in this 1 ohm, there is no current flowing in this 2 ohm, because both have come to 0. So what is the net voltage out here? It will be -2. Okay, why is it -2? Because there is no voltage drop across this 1 ohm and 2 ohm, and if you see, although it is given plus here, minus here, but the magnitude is given as -2. Okay, so you need to be careful in your exam. Okay, don't just purely go by the sign which is here. You also need to see the magnitude which is given here. So -2. So in the first case, we got Vz is equal to -2 and Ix1 and Iy1 as 0. Is this much clear to all of you? Dheeraj, is it okay?
Yes, sir.
Yeah. Okay. Now in the second case, what we are going to do is we are going to short this source and keep this current source. Okay, so in the both these cases, see, the dependent sources are not disturbed. Okay, so the dependent sources are kept as it is. Okay, now we have made one current source. Now we try to find what is the loop equations and try to compute. Now here again this is the voltage 6 x2, and y2 is the y2 is the current through 1 ohm. So the first equation x, why I am writing x2 and y2 is this is because this is just a second case. Okay, it's not the first case, it is the second case. Here I am writing y1 because this is the first case. So there are two different cases for the same circuit. Okay, now essentially iy means this is the current. Okay, for the second case I am prefixing it with 2. So 6i2, that is the voltage, this is the current flowing through. So 6i2 is the 6ix2 is the voltage, and iy2 is the current, which is, so this is one equation you get. Similarly at this node, if you see what are the currents which are coming is 11 amperes is the current which is coming into the node. So 11, and what is going out is ix2, right, ix2, and this is again coming in. So that is 2y. They have written a minus out here. So you get two simultaneous equations, right? So with this you can get a value of ix2 and excuse me, is minus 1 and minus 6. Now you need to also compute the value of this is the actually the problem statement is to find an Vz. Okay, so you have to find out this voltage across. Okay, so how to find that voltage? If you see, if you write a loop equation out here in this, right, it is 2 ohms. If you going top ix2, then 1 ohm iy2 y9, and Vz is equal to 0, right? And then we already have computed the value of ix2 and y2. If you put these values here, you get the value of Vz as 8 ohms, right, 8 volts, right? Now superposition theorem says that it is the algebraic sum of these two. So ix, in the first case we got ix1 is equal to 0, so this minus 1 will be minus 1. The final answer also will be minus 1. And iy, again iy1 in the first case was 0, so this becomes 0. iy2 is minus 6, so iy I get as, this is the final answer, I get it as minus 6 ampere. And Vz, so initial, in the first case we got it as minus 2 volt, in the second case 8. So if you add it up, you will get 6 volt. So this is how the superposition theorem helps us in solving problems in which there are more than one independent sources. Okay, you take one at any given time. Okay, only care needs to be taken is all the polarities which is given. You need to be careful about that, and also don't try to take this as a dependent source and make a third circuit out of it. All the dependent sources will remain in every circuit. Okay, so these are the common things which you need to take care. Is it okay? Okay, so let's move. So what are the limitations of superposition theorem? Like the other theorems, Norton theorem and the Thevenin theorem, again it is applicable only for linear circuits. Okay, this is a common limitation of all the three circuits, and also there must be more than one source. Okay, in this case, because this theorem itself is based on the fact of linearity, where you have two sources, and at any given time we are analyzing one source at any given time. So obviously there has to be more than one source to apply this theorem, right? So this becomes a limitation, that it is there must be more than one source to apply this theorem. Okay, so let me just give you one simulation video, and let's see what. See, this is a circuit out here. You have one voltage source here, and you have one current source out here. So this is an circuit again from here, derived out of here, in which this has been kept open out here, right? This is the second circuit in which this voltage source has been shorted out here. So if I play this circuit, right? Okay, so if you see here, say let's take any element for that matter. Okay, so the beauty of this circuit is you can compute the current or voltage across any of the elements. Okay, now if I take this 20 ohm resistor, see, if I do this analysis here, I get 1.63 ampere. Here it is 2.2 ampere, and this is 388 milliamperes in the reverse direction. So if I subtract 388 milliampere from 2 amperes, I will get 1.63. Okay, so if I talk about this, if you see the voltage across this is 39.5, whereas in this it is 11.6. So if I add both of them, I will get an 51.2. Okay, in decimal there will be small errors because of the simulation approximations. So if you see the voltage, okay, so if I talk about this 1 kilo ohm, it is 69 milliampere here. Here it is 38.8 milliampere, and here it is 31. If you add these two, you will get this. Okay. Similarly, the voltage, it is 31 here and 38 here, it is 69 here, right. So this is how superposition theorem works. This is the main circuit. I have split it into two different circuits with one source at any given time. So I can find out the branch currents and the node voltages, branch currents and the node voltages, and then if you do an algebraic sum, you will get the branch currents and node voltages of the main circuit. Okay, for every element, it will match. It will match not only for one particular. So when we are doing Thevenin's theorem and all, we were more focused on trying to find out the output voltage across 1, 2. Here, once you solve these two circuits independently, you can find out what is the current and voltage across any one of them, right. You just have to take the corresponding voltages and currents. You need to just do an algebraic sum for any of the element. Okay, so that is how superposition theorem works. Okay. So let me show one more video. Here if you see, I have connected an diode. So we said in superposition theorem that it has to be bilateral and linear. So this is obviously not a linear circuit, because I have put a diode in this place, right. So if I do the simulation, see, in the first place I am putting an 100 volt here, out here. So that will ensure that this diode is an forward biased. Okay, so this loop is activated. So you will find some current. There is a current source here that is also pushing in some current out here. So you have some total of 7.3 ampere flowing into this 10 ohms resistor. Okay, there is current coming from here, there is current coming from here, both the things. Okay, whereas when I split these two circuits, now here I am taking only the voltage source. I am keeping this 5 amps open. Okay. In this case, there is you still get the correct results, because this diode is forward biased, and there is a current flowing like this. Okay. Whereas when I am using only the current source, this diode gets now reversed biased, and you will see 0 current into this path. Okay, that is actually not the case, because when you have 100 volts, so this diode also appears like a short circuit here for the circuit. Okay, there will be small voltage drop across that, but then when the current source will pump in some current here into this circuit also. So you see this in this particular simulation, you will have only 0 current here. Okay, that is because this diode is not bidirectional, it is a directional element and non-linear element. So the superposition theorem does not hold good here, and if you take the sum of these two currents, obviously it will not match here. So here it is 7.3 ampere, it is just 4.72 ampere and 5.1 ampere. So if you add it up, it's not matching with the results here, right. Similarly, here it is 0 ampere, whereas here it is 2.43 ampere, right, because now there is no reverse current flowing into this, right, from this source. So so that is why there is a difference out here, if you can't add these two and get this here. So obviously, why is the amp yeah, let me take on that question. Yeah, Gagan, why is the amp case the values is 5.1?
So when you split it, sir, that there are some.
Okay. It should be 5. Actually, in this particular software there is an I can't feed the number, there is a dial, so I have to just set it at 5. So while I was doing that, probably I was not careful, so it got set at 5.1. okay, but that doesn't make for your understanding purpose this. Okay, so this is all for today. In the coming tutorial, I have put a lot of examples on superposition theorem also, so that will make the things more clear to all of you. Okay, thanks a lot. That's all for today.